Hi all. Okay, so we're back again. This week we're going to be looking at the format string vulnerability. So, as usual, first I'll give a bit of background about format functions and specifically the with the format functions that are within the C standard lib. Then we're going to look at the format string vulnerability, and we'll take a look at the code that we've mentioned last week that we found on the CWE website, the example code. We're going to actually I'm going to go through a demo and write some code to demonstrate exactly what format functions in C are capable of, and I'll introduce some vulnerable code. And next week next video we'll we'll exploit it. We'll be going into the exploitation section. I want to give you some time to actually mess around with it yourselves in the meantime before giving you a I don't know, like a walkthrough guide on how to exploit format string vulnerabilities. Okay, so format functions. So format functions are used to insert formatted data into a string template. So you might have some familiarity with the concept of a format function if you've done any programming in any high-level language. Pretty much there's format functions. So they are made up of two components. You've got a format string, which is a string which has some placeholders within it, and then you pass a list of parameters that you want to fill in those placeholders according to a predefined format. So they're common across programming languages, but they can be a problem in C, C++, basically the languages that let you manually manage memory, so they can appear in Objective-C as well, and like languages that let you, because you can run C standard lib functions within Objective-C, and you can do like manual memory management there too. So they're still actually, despite being discovered in the early 2000s, they are still prevalent and being discovered. There was around 20 CVEs issued in 2020. If you have a look on the, if you look on the CVE database, you can find, and you search for format string, you can find loads of examples. So I'm gonna just drop in and give you a demo on some. We'll do a bit of coding. Give me 2 seconds. Alright, cool. Okay, so first thing we can do is take a look at the man page for Printf. So Printf is used to format and print data. This actually looks incorrect. So, okay, right. Okay, so this looks like this looks like there's a utility called printf. So if you look for the man printf, it's actually pulling back the man page for this command. So we can find where it is. If we do where it is printf, we can see that there's a binary called printf. Alright, so that's not what we want. So what we actually want to do is, and this is a trick for if you're using the man pages in Linux, if you put man3, it pulls back the developer documentation. So we can go man3 printf, and this will give us the Linux programmer's manual. It gives us, so we can see printf, here are the function definitions. It tells you what library they're in, and there's loads of different variants, as you can see. So printf by default prints to standard out, and so does vprintf apparently. So we've got the functions printf and vprintf write output to standard out. These other variants do different things. So we've got fprintf looks like it takes a format string, variable length arguments, just like, and it prints to a file stream, a file object. Same, it looks like this dprintf prints to a file descriptor. Sprintf actually prints to a pointer, to a character pointer, so a string. And snprintf has, so snprintf actually has some bounds checking in. So it does the same thing as the sprintf, except for it has bounds checking. So that's useful if we want to avoid things like buffer overflows. But for this particular vulnerability, it actually doesn't matter. It's not related directly to passing too much data into the function and overwriting a buffer. It's actually something slightly different. It's a bit more. We'll get to it, and it's an interesting problem, and it actually comes down to the fact that these functions allow you to pass a variable length amount of parameters, and the amount of parameters that the printf function looks for when it's filling in its templates are determined actually by the string and the number of template characters within the string, not by the amount of parameters passed. And this can be ends up being a huge problem, because it's a massive problem if the user has any control over the format string itself. So if I can say, so I'll give an example. We'll just write some basic format printf, some basic code with some printf statements. We'll just give it a file name. Let's see. Okay, so we'll include standard IR h, and then we need int argc character argv. Alright, so we've got a main function, main method. We'll just do something very simple, just the bog standard. Everyone's done it before. And we add a new line at the end. So we'll printf hello world and then return 0. So, alright. So we've got a very basic C program. All this does is uses printf. Because printf has a variable amount of a variable amount of parameters, we can pass it just one parameter, just a standard string with no format placeholders at all. All we're doing is just wanting to print hello world and a new line character, and then we're returning 0. Okay, so let's compile it. So we can go gcc, in order to demonstrate this, I'm going to pass a bunch of parameters to GCC which remove the security features, just so that we've got so there's no address space layout randomization that ends up messing with our the memory addresses. So it's easier to just see what's going on really, and I'm going to force it to so G includes your debugging symbols. It's useful if we look in GDB. We can do M32 to make it 32-bit binary, which makes it easier to read, and we'll build up to 64 eventually, but it's a lot easier to start with 32 bits. We'll also we'll make the stack executable, which is useful if we want to exploit it. We will also do no pi, no fpi. This is the ASLR stuff. We actually have to do one more step before we do this, so let's just add a comment there so that we can come back to it. Okay, so to disable ASLR temporarily on Linux, what we need to do is we need to set a parameter in the proc sys kernel. So we can do this. So we'll need to be a super user, and because we're using the redirect, because we're redirecting from echo to the randomized virtual address space. Yeah, so because we're using this redirect, we can't just say echo. We can't do sudo echo 0 and then redirect to the kernel randomized VS space, because the section after the redirect requires super user access. So you can just launch a command, which you can launch a command with bash-c and sudo bash-c, and everything within the single quotes will get executed as super user. So that's not my password. Yeah, that is the password. Okay, so we can't actually do it. Right, yeah, I made another account in this system. Let's just ignore that. I'm pretty sure I may have already set this earlier. I'll just have to check. Give me 2 seconds. Okay, so I just switched to a super user account and set that command line parameter. So yeah, you need to echo 0. You need to store the value 0 in this file in order to disable this ASE temporarily. Right. So to go back to where we were before, we were compiling just compiling our hello world program, so we can go. We can reuse this later. It'll make it wasn't executable anyway. It was exec stack. So we want to have an executable stack, which is actually like all these things I'm doing. I'm disabling the memory protections that have over time built up and have been added to make an attacker's life more difficult. We can't. These all have bypasses, and we can eventually later in this in the term and the module, what we're going to do is we're going to go over what each of these actually does and how you can avoid. What you can do to get around it, basically. So we'll do no rel, we'll do m32, and we'll set the stack boundary so that if we set the preferred stack boundary, it doesn't add extra instructions in the binary to align the stack. So it's actually a lot easier to read what's going on. There's less noise, basically. So we add demo.c and we'll output and we'll call it demo. Alright, so demo, hello world, cool. We're all good so far. Right. So that's our basic printf statement. It doesn't do much. All it does is print hello world. What we're going to need to do next is we need to add. Let's first just pull this out in. So in order to demonstrate that you can pass parameters into printf, we can pull out world. Let's say we want to say hello. We wanted to use someone's name. Let's not call it word. We'll call it name. So we can create a character, a pointer to a string that we've hard coded. So we'll call it name, and we'll just hard code Tom, just to demonstrate what's going on here. So, right. So what I've done here is I've added this. This is actually really small. Hopefully that's a bit clearer. Yeah, sorry about that. Hopefully it's not too bad at the start. There wasn't much there, just hello world. Okay, so now what we've done is we've pulled out this. We've pulled out the word world. We've changed it. We've replaced it with this string Tom. So we've got a pointer to a character pointer to this. This will point to the memory address that the first letter T is at. So then what we're doing here is what we're saying. We want this. We want to print hello, and then we want to replace whatever this is with whatever this variable points at. So what printf will do is printf will grab your string. It will start looking through each letter of the string, and it'll come across this. It'll come across this %s, and it'll be like, I need to have a look at. I need to have a look at what's in the contents of this variable. So it does this by, when you actually call the function, these parameters get put on the stack. The call stack is essentially the thing that keeps track of the program as it's running at runtime. So if you call a function, it gets added to the stack, and all the things that you pass into that function get added to the stack too. So when we call this printf function, it will add this string to the stack. First it will add this parameter to the stack. Then it will add this string to the stack. If we had another parameter, it would add this. Like this is not going to work, but this would get added first. This would get added second. The reason being, the stack is a first in, last out data structure. So think of it in terms of, like, I think the example in the lab sheet is a stack of plates. So you put your first plate on, your second plate on, your third plate on. You can't actually get your first or your second plate until you pop the first plate off the stack. You can push things to a stack and pop things from it. Right, so what we're doing here is we're calling this function, we're pushing this to the stack, then we're pushing this to the stack. Then the function runs. When the function runs, it iterates through each letter in this string. It finds the percentage sign, then it realizes, right, I've got some formatting that I need to do. So it makes a decision based on the next character. The next character is an S, so it's saying, okay, I need to pop a string from the stack, convert it to a string, and then stick it here. Need to replace this in memory with the string. Right, all so far so good. So we can compile this and have a look at what happens. We can just use the same compile string as before. We'll just build up on the same program. So we run the demo. Now we've got hello Tom. Cool. All as expected. So what else can we do with it? Well, what else can we do with format strings? So we don't just have to replace strings. Like the main use for these kinds of things is like actual formatting. So things like rounding numbers to a certain amount of decimal places. So we can do that one. We can go. Imagine like you're scoring someone's grade in terms of a percentage, and well, yeah, we'll go like this, for example. So this is your grade, and you're all going to get 89% at least. Alright, so what we can do is we can say you achieved, and then a percentage. So, as you probably realised, if the percentage is the delimiter for the format string, we're going to have to escape this somehow in order to print an actual percent, because we would like say we wanted to print like 89.14%. That's what we're hoping that this is what we get when we print the string. So in order to do that in printf, double percent will do it. For now I'll just quickly compile and just double check, but okay, so yeah, double percent adds the percentage. Because we've not added a new line on the end, we're now in this situation where it printed to the start of the line. It looked a bit dodgy, so we'll just add a new line just whilst we're here. Quickly, go again. Right, cool. You achieved percentage. Right, how do we get? Now what we need is we need to pull this number in, and we need to format it to like 2 decimal places, because we don't really, yeah, we just want to format it to 2 decimal places. So what we can do is we can use because it's a float, it's %f to represent the number, but because we only want 2 decimal places, before the f you can put like a dot, a period dot, and you can then pick how many decimal places you want to put. So we can do 2f, and in this case we'll just do 2f, and we will do this, and we don't have a problem. Okay, we have a problem. Why is it showing 0? The reason is because we didn't actually pass the parameter in. So in order to pass the parameter in, we would go your grade. Right. Okay, so you achieved this. There's a space there. We'll get rid of that space, but I'm not going to bother compiling just to show the space. So if we get rid of that space, then this actually we will do. Why not? While we're there, it takes 2 seconds. Right. So you achieved 89.14%. Cool. Well done. You got first. Right. What next? Right. So we want to look at things. So we can do things like format it in hexadecimal. So if we do this, we can, like, an interesting thing that we might want to look at is where this variable is stored. So we might want to look at, yeah, where this is located. So we can actually like print out the memory address of this variable, and we can format it in hexadecimal. So we can do, so we'll say name, or we can even say, like, we can do this. Oh god. So in order to put, we have to escape these strings if we want to use double quotes within the string, but we'll say Tom, the string Tom is at memory, memory location, and then we want to do, we'll call it address. And then we want to print it in hexadecimal. Okay, so %x lets you print in hexadecimal. A common convention for representing hexadecimal numbers is this, like usually they're like OX, FFFF. So OX lets you know that it's a hex number ahead of time. We can add that in just to follow convention, and now we actually need to pass the parameter in this time so that we don't get funny behavior. In fact, it might be interesting. This one will be interesting because this shows the vulnerability actually. If we don't actually pass, okay, so I was going to explain this later, but I'll just show you that this gives you some, this is actually a problem. This hasn't introduced the vulnerability, but this is a bug. Like this is not, this isn't going to do what I expect it to do, right? Because we've told printf here that we want it to pop the next instruction. Essentially, what we've told it to actually do is pop the next instruction from the stack and shove it here, and then shove it here in the string, and then print the string to stand it out. So the problem is we've not given it anything to pop from the stack to put in here as hexadecimal. So what it's going to do is it's just going to grab the next instruction from the stack. So it's going to just pop whatever's on top of the stack and then just print that. So if we, which is really bad because we can, we'll see why it's bad in a bit. Okay, so that isn't correct. So this is just printing whatever's next on the stack. So this is a problem. So if we want the actual correct memory address, we can look. We want to see name, and we want to use the address of operator. So we want to know what the address of name is, and then we want to format it into hex and print it here. So let's try to compile that. See what happens. Okay, so that looks more like it. Cool. Right. So we've printed stuff in hex, and we have. Okay, so yeah, we've done hex, we've done decimals, we've done normal strings. What else can we do? So right, this is the dangerous. This is dangerous. What we already discovered is there's a dangerous way of we can leak memory by not provide. If we don't provide the parameter, the function is just gonna start reading from the stack and printing it out. So what we can do is. That's obviously a problem, but there's another massive problem, and this is actually the real bad problem. This is what turns it from just like a confidentiality problem, where it's just leaking data from the stack, into actual like a super serious critical security vulnerability. Well, if the user controls the input. So for now, we're not going to give the user control of the input. So we'll get there eventually, but this particular placeholder is the main problem. So %n. So what does it do? Let's have a look. Okay, so we're %n. Okay, so this is in the bugs section for a start. Oh yeah, if you just wondered what I did then, to jump there, it was I did / and then you need to escape percentage signs. So I did /, so / / to search, then / %n to search for a %n in the document. It highlights it. Cool. So bugs. So code such as print foo often indicates a bug, since foo may contain a percentage character. If foo comes from untrusted user input, so this is the problem. If foo, which is our print string here, comes from untrusted user input, it may contain a %n character, causing the printf call to write to memory and creating a security hole. Right, so this is obviously dangerous. So this %n allows us to write to a memory address. Hang on a second. God. Alright, that's funny. I hadn't seen my. I wonder how long that's been doing that for. I'd not looked at my camera for a while, but apparently my green screen, like the chroma key, was just like taking half my face away. Alright, cool. Okay, so %n is not good. What does it actually do though? Like, let's have a look up here. So n, the number of characters written so far is stored into the integer pointed to by the corresponding argument. So, and I'll just give some example code to make it clear. So basically what this does is it counts the amount of characters that have been printed out so far in that print statement, and then it writes that to the parameter that you give it. Okay, so this is super dangerous because we can, if you can control where you're writing to memory, then you can, if you can control the print string, you can use the %x to read from arbitrary memory, and you can use the %n to write to arbitrary memory. But for now, I'll just give you an example of like semi-legitimate use. I think this is a really dangerous function, and it shouldn't be used at all. Like, it shouldn't be. Well, it should be carefully used. I don't think that this. I think that, yeah, you need to take caution and don't give the attacker control over the actual print string, like the actual format string. It's really, really bad. They can do lots of like dangerous stuff with it. So we can do something like, I don't know. Alright, so we're just going to print the alphabet out because we know that's got 26 letters. And we hope this is correct. And then we'll do a new line at the end. And we want to print that. We want a variable that we can print to. So we can call it like in, we'll say number of characters, and we'll initialize it to 0. And then we can say number of characters. Alright, so I think we actually need to give it the address of the number of characters. So what this is going to do is it's going to count all these letters, then it's going to say, right, oh, it wants me to count that, so it's going to iterate through, print all these letters. When it hits there, it's going to be like, right, %n, okay, I need to figure out how many characters I've printed, and then I need to store it here in the next parameter that I've got to pop off the stack, right? So some legitimate use cases other than this, which is just okay, so that would actually store it. We want to, before we compile, we want to make sure that we can see what's in the variable. So if we want to look in that variable, we can just say number of characters, and then we can print it out as decimal. So there are table. I know I didn't actually show the table, but I showed the n in the man page. But yeah, there are tables which show all of these characters, all the placeholders. So there's things like this, like these are the ones that are used mostly. It's like formatting floating point numbers or longs or like strings or I don't know, D. Well, let's actually, I need to double check D actually. I wonder if that's going to get it. Nope. Let's have a look. I don't remember precisely what it is. Alright, yeah, so it's just integers, signed decimal. It uses signed decimal. Okay, so integer and D. Yeah. I knew it was for printing it, I just wondered what they actually represented. D, I guess the decimal makes sense, signed decimal. Alright, so let's go back to the code very briefly. So what we're expecting this to do is, whoa, I just actually noticed this. That's not correct. Okay, right, so what we wanted to do is we wanted to count how many letters have been printed. I've not compiled. GCC, don't know, yeah. Right, so we have a compiler error. Of course we do. Because I've not ended the line with a semicolon. Alright, cool. So what it does is counts that, %n sticks it in, sticks the number that, of characters that have been printed in that number of chars variable. Then we're then printing out that number of chars variable. So we can see that we've written data to the stack that's based on the format string, right? We've written some data to some memory address that's based on some format string, rather. Now, all of this is bad practice, but it's not technically exploitable yet because we've not actually given the user any control over anything. This is all just hard coded at the minute. So what we can do next is actually start pulling some of this stuff out. Oh, actually, first I'll just because yeah, we'll start pulling this out because I want to get close to the example that we looked at the other day. I'll add a function. And we'll look at the example again in a minute. Okay. So we can actually print this string out and then replace this. So we can, let's say we just want to print our name out. We can do this, and all this is doing is, when we get to the end, we're then calling this print wrapper function that we've just created. We're passing it the character pointer name, which then gets locally assigned to the string variable, which we're then passing directly to printf. And here, this is bad use of printf because we're not passing in this. We're not passing in any parameters. Okay, so this is bad use of printf. Compile it, run it. We forgot the new line, but I suppose it doesn't matter that much. If we did add a new line there, we would then end up with like a new line here and an exclamation mark on another line. So this is getting quite messy. Right, so that's all the programming constructs are there pretty much now. We've got a function. We've demonstrated what we can do with the printf function, and now I will introduce a vulnerability. So let's just actually let's simplify this code a bit. We've got a lot here, so we don't need any of this anymore. We know how this works. We know how this works. We know how this works. So all we've got is name Tom. Yeah, that'll do. That'll compile. Okay, so all that's going to do is just, and let's just add a new line just so that it looks nice. Right, so yeah, all we're doing is printing Tom. It's calling a function. Oops, compiled again for no reason. Cool. Right, so how do we make this actually exploitable? Alright, we need to give control to, we need to have some user input. So how do we get user input? Well, we could use getS, but we know getS is a very dangerous function. And we don't want to introduce two vulnerabilities at the same time because it might end up, we just want to focus on one thing, right? We want to just focus on what the problem with the format string vulnerability is. So we'll add a buffer, winded buffer. So print me, we'll make it big because we need enough space on the stack to actually throw some shellcode into so that we can exploit it. If we look back at the, oh, in fact, yeah, okay, I'll introduce the vulnerability and then no, actually we'll do it now. Okay, so we'll go back to the slides. Bear with me, sorry. Okay, so we're back, right, cool. So, interestingly, as we've seen that printf is a powerful function, it's actually Turing complete. So that means that you can technically represent any theoretical Turing machine within the function. So that basically just means that it's computationally universal. You can do anything that you can implement an instruction set architecture in it. You can implement virtual machines in it. You can make games. You can do whatever, right? And so it sounds unreal, like to think you can just do that with a printf statement. But there are some examples, right? Oh, I had it the wrong way. Let's move that over there. Cool. Yeah, so there's two really good examples. Three, there's more, there's loads, but these are the two that I think are worth pointing out. Are the Printf Tactor, which is by Carlini, who has done a lot of work in this area, where he was part of another project which implemented a programming language interpreter, whose name I won't repeat here, in just a printf statement, right? So this one's cool because they actually, in the GitHub, if you go into the repository, they actually they formatted the source code so that it's got a percentage n. Yeah, just to demonstrate that's what the power of introducing such a function into a language actually does. It's really, really wild. So they, oops, sorry. So Carlini created this tic-tac-toe game. Google took it a step further and they actually implemented a full virtual machine which had they had their own instruction set for it, and they made this little maze game where you had to like find the shortest path around or something. It was in their qualifiers for the Google CTF 2020, and the challenge was called Sprint, and it used sprintf, and you had to do some reversing to find out what the desired input was. There's a link in the description and in the references to both of those projects. They're really cool, worth having a look at. They'll bend your mind. Alright, so yeah, so as I said, we were going to get to this. Last week we saw this on the CWE website, some example code. It actually didn't compile. Oh no, sorry, it did compile, but it immediately gave you a seg fault because of some incorrect referencing. I'm not sure if that was intentional to make it so that it's harder to compile so that people can't actually accidentally misuse it, but I'll assume so. Okay, so we'll go back briefly to the demo. Now we'll okay, so I'm not going to do that for now. I just remembered something that I'd missed earlier, so I'll quickly just I'll leave the writing of data to specific locations in the stack for the exploitation video that's going to come out in a week or two. Just what I think we should do. I'll just quickly show you. It's important to know, but essentially printf. I think I might have mentioned it. I'm not sure if I did. I can't remember which take made it into the video or not. But yeah, if you have a variable here, let's just go with this for example. Let's just imagine that A and B are strings. So we don't have to actually run this, but let's just imagine. Well, yeah, I'm not even going to bother writing. Let's just imagine. Pardon me. A and B are values on the stack. The point I'm trying to make is this value gets added first to the stack. So they get the parameter values get added right to left onto the stack, right? So B will be first, A will be added on top, and the reason being is that because a stack is a first in last out data structure, when we get to the first S, we want to pop the first value, the A, from the stack. Then we hit the next %S, then we want to pop the B from the stack, right? And then if there were further characters, we could pop those as well. Yeah, I'll leave the actual usage of %n for exploitation until next week because this is already a really long video. I don't want to overdo it. So I'll just quickly drop back to the slides. Right. Okay. Yeah. So we'll just do a recap quick. So format functions are Turing complete within C and C++ anyway. You can read to arbitrary memory with %x, and you can write to arbitrary memory with %n. So the format string itself controls program execution. If the attacker controls the format string, you can get arbitrary code execution, and that's just obviously not good. Disaster, worst case scenario, even worse if it's over a network and it's remote. So format strings are a critical security vulnerability. Hope that was interesting. Hope that was interesting and useful. They're not always a critical security vulnerability. I misspoke, but yeah, they can be if implemented, and it's really easy to do so. Okay, so the references here, there's some interesting ones. Most of this comes from the John Erickson textbook, Hacking the Art of Exploitation. Really good book. Yeah, there's the various usages of printf there. There's some other resources that are really interesting as well. and thank you for listening. Hopefully this was interesting. Cheers.